Hey there, Mr. Sutton here, bringing you the BC Calculus 617 Part 2 homework solutions on Euler's method. For this problem, we've got y equals f of x as the solution to a differential equation dy over dx equals f prime. We have an initial condition of f of 1 equals 5, and we've got some f prime values in the table here. So we want the approximation for f of 2 with Euler's method on a step size of 0.5 starting at 1. All right. So we need to get essentially from f of 1 to f of 2. They told us f of 1 was 5. We need to figure out f of 2 in 2 steps, which means we first need to figure out an approximation for f of 1.5, and then use that approximation to figure out f of 2. So we'll start with f of 1.5. Using Euler's method here, that's going to be f of 1, which we know, plus f prime of 1 times our step size of 0.5. So that's going to be approximately, let's see, f of 1 is 5, and then our derivative at 1, well, given our table here, we see that f prime of 1 is exactly, let's see, 0.5 right here, this value here. So we've got 0.5 times 0.5. So this is 5 plus 0.25, which is 5.25. And now we're going to figure out f of 2 based off of this. So f of 2, that's going to be our approximated value at f of 1.5 plus f prime of 1.5, which we can look up in the table, times our step size, which is still 0.5. So f of 1.5, we just approximated that to be 5.25. And then f prime of 1.5, that's in the table here, that's 0.4. And then we still have our step size of 0.5. So this comes out to, let's see, 0.2 over here. So we have 5.25 plus 0.2, which is 5.45. So careful adding those decimals. And that ends up giving us choice B. On this problem, we have a differential equation x plus y, an initial condition of 1, 2, and we want to figure out f of 2 with Euler's starting at 1, going by a step size of 0.5. So first we need to figure out f of 1.5, and then we'll use that to figure out f of 2. So f of 1.5 using Euler's, that's going to be f of 1, which we already know, plus f prime of 1 times our step size of 0.5. F of 1 they gave us, that was 2. And for f prime of 1, we're going to need to plug 1 into our derivative up here. But if we have an x value of 1, we also have a y value of 2. So we're actually doing 1 plus 2 if we're doing x plus y. And that comes out to our derivative at 1, that is 3. So this is going to be plus 3 times 0.5. 2 plus 1.5 comes out to 3.5. So this is the value of f of 1.5, or at least it's approximated. Now we're going to find f of 2, and we're going to use our value at 1.5 plus the derivative at 1.5, which we're also going to have to estimate now because we're using an estimated y value, and we still have a step size of 0.5. So at 1.5, our estimated value there was 3.5. And now to get f prime of 1.5, we're going to use an x value of exactly 1.5 in the x up here. But now we have to use our approximated y value of 3.5. So we're doing 1.5 plus 3.5 if we're doing x plus y. And that comes out cleanly to 5. So this is going to be 3.5 plus 5 times 0.5. So this is 3.5 plus 2.5, which comes out to 6. Choice C. On this problem, we're given y of 1 equals negative 3 and a differential equation here, 2x plus y. We want to figure out y of 2 using Euler's with a step size of 0.5, starting at the 1 that they gave us for an x value. So we're going to start by figuring out y of 1.5. We're going to approximate it, and then we'll use that approximation to figure out y of 2. So we're going to have to do this in 2 steps with Euler's. So starting off here, y of 1.5, that's going to be y of 1, which they gave us, plus we're going to have a y prime of 1, whatever that comes out to, times our step size of 0.5. So y of 1, they told us was negative 3. And now for y prime of 1, we're going to have to plug 1 into this differential equation. That also means we're going to have to plug in the y value that goes with an x value of 1, since when y is 1, when x is 1 rather, y is negative 3, we're going to be doing 2 times 1 plus negative 3 for the derivative at x equals 1. So this is going to be 2 minus 3, which is negative 1. So we've got minus 1 times 0.5. Negative 3 minus 0.5 essentially is going to come out to negative 3.5. So that's our estimated value for y of 1.5. Now we're going to use that to find y of 2. Y of 2 is going to be this estimated y of 1.5 that we just found, plus y prime of 1.5 times our step size of 0.5. So y of 1.5, we just figured out that's approximately negative 3.5. So this is an approximately equals. Plus, well, now we need the derivative at 1.5. So for this, I'm going to be plugging the x value 1.5 and the y value negative 3.5 into my differential equation. So this is going to be 2 times 1.5 minus 3.5. And that's going to be 3 minus 3.5, which is negative 0.5. So over here now I've got minus 0.5 times 0.5. So this is negative 3.5 minus 0.25, which is negative 3.75. This was a no calculator question, so careful with your decimals. And that comes out to choice D. On this problem, we've got this differential equation 2x plus y, initial condition f of 1 equals 0, and we want f of 2 with Euler's with 2 steps of equal length starting at 1. So let's see, if I'm starting at f of 1, I need to find, if I'm doing this in 2 steps, I need to find f of 1.5 first. Then I'll use that to figure out f of 2. So we're going to use a step size then of 0.5 if we're going from x equals 1 to x equals 2. All right, so I'm going to start with f of 1.5. I need to find that first. That's going to be f of 1, which they gave us, plus f prime of 1, which we'll have to figure out, times we said our step size was 0.5. f of 1 they told us was 0. f prime of 1, I'm going to be plugging 1 into my differential equation. The y value I'm going to have to plug in is 0, because when x equals 1, y equals 0. So f prime of 1 is going to be 2 times 1 plus 0, which is just 2. So over here then I've got plus 2 times 0.5. And the decimal math is not going to get much easier. This is just going to be 1. And now we move on to figure out f of 2 based off of that. So that's going to be f of 1.5, or approximately f of 1.5, plus f prime of 1.5 times our step size of 0.5. f of 1.5 we just found was approximately 1. And then f prime of 1.5, well, I'm using my differential equation. Now I have to plug in the x value 1.5 and the y value 1. So I'm going to do 2 times 1.5 plus 1. This is going to be 3 plus 1, which is 4. So this is going to be down here plus 4 times 0.5. We've got 1 plus 2 essentially, so that's going to be 3, which gives us our answer choice of D. For this problem, I've got a table with values of f prime, and I'm given the value f of negative 0.2 equals 1. We want f of 0.4 approximated with Euler's using a step size of 0.2. All right, so if I'm going from negative 0.2 to positive 0.4 with a step size of 0.2, that's going to be 3 steps. I'm going to need to find f of 0, f of 0.2, and then I can finally use that to approximate f of 0.4. So starting at the beginning, f of 0, that's going to be f of negative 0.2, which we know, plus f prime of negative 0.2 times our step size of 0.2. F of negative 0.2 they gave us over here, that's 1. And then f prime at negative 0.2, we can look that up in the table, which conveniently has values for everything we need for f prime. So that's going to be 0.8. Step size of 0.2. This is going to be 1 plus 0.16, so 1.16. And this actually was a calculator question, but so far we haven't needed one. So moving on now, we're going to find f of 0.2, and that's going to be f of 0, which we just approximated, plus f prime of 0 times the step size of 0.2. F of 0 we said was about 1.16, and then f prime of 0, that's going to be 1.2 from our table, times our step size of 0.2. So we've got 1.16 plus, let's see here, this is going to be 0.24. So that adds up to 1.4 so far. Feel free to wimp out at any point and use a calculator. There's no shame. Moving on now to f of 0.4, the final thing that we actually wanted. this is going to be f of 0.2, which we just approximated, plus f prime of 0.2 times a step size of 0.2. So f of 0.2 we said was 1.4. F prime of 0.2 from our table is 1.7. Still have that step size of 0.2. So this is 0.34 over here that we're adding to 1.4. That's 1.74 altogether. And that finally gives us answer choice B. For this problem, we're given the differential equation x minus y with the condition of f of 2 equals 8. We want f of 3 approximated with Euler's using 2 steps starting at x equals 2. So since we're using Euler with 2 steps, we need to first find an approximation for f of 2.5, and then we'll use that and launch off of that to find f of 3. So starting with f of 2.5, or 5 over 2, and the reason I'm writing 5 over 2 is I'm looking at my answer choices on this non-calculator problem and noticing the fractions. So, when in Rome, do as the Romans do. We're going to start with f of 2, and then we're going to add f prime of 2 times our step of 0.5. F of 2 they gave us, that's exactly 8. To find f prime of 2, we need to plug 2 into this differential equation, which means we also have to plug in the y value that goes with it, which is 8. So this is going to be 2 minus 8 for f prime of 2. That's negative 6. So over here now I've got minus 6 times 1/2. So we've got essentially 8 minus 3, which comes out to 5. So that's our approximation for f of 2.5. Now we have to approximate f of 3 using this value. So for f of 3, I'm going to do f of 2.5, which we just kind of approximated here, plus f prime of 5 over 2, or 2.5, times a step of 1/2 still. F of 5 over 2, that's approximately 5. We found that earlier. F prime of 5 over 2. Now we're going to have the x value 5 over 2 minus the approximated y value of 5. So 5 over 2 minus 5, well, that's essentially 5 over 2 minus 10 over 2, so negative 5 over 2. So this is going to be minus 5 over 2 times 1/2. And let's see, this is going to be really minus 5/4 if we multiply that out. So we have 20/4 minus 5/4. That's going to be 15/4, which gives us choice C. On this problem, the next few problem parts are going to use this differential equation right here, kind of, sort of. The first part doesn't really use this differential equation per se. It uses the slope field based off of that. So for this one, they just want us to sketch a solution curve that goes through 0, 1, which they've put a dot on our map here, and also another solution curve that goes through 0, -1. So let's start with the one that goes through 0, 1. We essentially have to follow these tangent lines and go through 0, 1. The only way to do that is if we go in a straight line like so. So here's our solution curve for 0, 1. And now if we have an initial condition of 0, -1 down here, this is on a tangent line that's part of a more curved kind of pattern like so. So just follow those tangent lines and go through the point 0, 1 from one edge of the slope field to the other. For this problem, they're saying f is a function that satisfies this differential equation with an initial condition of f of 0 equals 1. They want us to use Euler's method starting at 0 with a step size of 0.1 to approximate f of 0.2. So to do this, we're going to do it in 2 steps. First, we're going to approximate f of 0.1, and then we'll use that approximation to get f of 0.2. So here's f of 0.1. That's approximately equal to f of 0, which we actually know the exact value for, plus f prime of 0 times our step size of 0.1. Plugging things in now, f of 0 we said was 1. And then f prime of 0, we have to plug 0 in for x in our differential equation, which means we also have to plug in the y value 1 that goes with 0 for this y up here. So f prime of 0 is going to be 2 times 1 minus 4 times 0. And we can write exactly equals because we're using exact values here that we know, but later on we're only going to be able to approximate the derivatives. So 2 minus 0 is just 2. So we have plus 2 times 0.1 over here. And there's no point not simplifying it because it'll just make things tougher down the road. So this is really 1 plus 0.2 or 1.2. All right. Now we're going to figure out f of 0.2 based off of this value. So we're going to say that's going to be f of approximately equal to f of 0.1 plus f prime of 0.1 times our step size of 0.1. F of 0.1 is approximately 1.2. Approximately equals, that is, because this is just an approximated value here, plus f prime of 0.1. That's going to be 2 times 1.2 for the y value, minus 4 times the x value, 0.1 over here. So 2.4 minus 0.4 is just 2. That's kind of convenient. So we've got plus 2 times 0.1. We have 1.2 plus 0.2 again, so that's 1.4, and that is our answer. On this problem, they want us to find the value of b, for which y equals 2x plus b is the solution to this differential equation. So for this one, the thing to keep in mind is that the y that you see up here and the y that you see down here, and really all the letters, are the same letters. Like this y and this y are exactly the same. So one thing we can do, and we're going to need a system of equations here, one thing we can do is substitute all of this stuff in for the y in the original differential equation. That'll give us one look at what the differential equation could look like. So distributing this, we've got 4x plus 2b minus 4x. And this is awfully nice because these 4x's just cancel out, leaving us with dy over dx equals 2b. So that's one take on dy over dx. Now, another way to express dy over dx is by literally just taking the derivative of this expression right here. If you take the derivative of both sides, that's also going to give you dy over dx. So what is dy over dx of 2x plus b? Well, b is a constant. So we're just taking then the derivative of 2x, which is just 2. So we're told that dy over dx equals 2b. It also equals 2. Well, that means that 2b and 2 must have the same value, which means then that b must equal 1. For this problem, g is a function that satisfies this differential equation with the initial condition 0, 0. We want to know if the graph has a local extreme, the graph of g has a local extreme at 0, 0, and if it's a min or a max. All right, so in order to see if you have any kind of local extreme, we first need to see if there's a critical value at 0, 0 when I plug this point into my differential equation. So we can say g prime of 0 equals 2 times 0 minus 4 times 0, because x and y are both 0, which of course all comes out to 0. So this tells us there's some kind of critical value there, and it's worth investigating further. If we hadn't gotten 0 or even like undefined, we would have said right off the bat that there's no extreme. But this is 0, so let's keep going. To do this, we're going to use the second derivative test. I don't know a whole lot about this first derivative, and I mean, you could try plugging in things to the left and the right, but that's kind of weird when you have one of these equations that has the output variable inside the equation. So we're going to go second derivative on this, which in general is going to be 2y prime, or 2g prime in this case, minus 4. So if I do 2g prime of x minus 4, and I plug 0 in for x again, now trying to find the second derivative at 0, 0, we've got 2 times g prime of 0 minus 4. Wait a sec, what's g prime of 0? Oh, we just figured it out up here. It's actually 0 again. So this is just 2 times 0 minus 4, which is negative 4. And the reason we care is that negative 4 is, well, negative. Since our second derivative came out negative, that means at this critical value we are concave down, which means we're at the top of a frowny face, which means this is going to be a max. So g then has a local max at 0, 0. And the proof of this is that g prime there is 0, and g double prime there is negative. And that's all we need to show that we have a local max by the second derivative test.